Hey everybody, Mr. Qualls, and I'm going to make two videos that support this lesson. It is about rational and irrational numbers, but we're going to start off with some rational ideas, some terminating decimals, some repeating decimals, and then I'm going to talk about power, or not powers, but yeah, exponents and roots in the next video that goes along with this. This one's just about this right here. So we need to be able to tell the difference between a rational number and a number that is not rational. A number that's going to terminate and one that is not going to terminate. And then do what we have to get our answers, okay? So a lot of times it helps mathematicians out if we understand what kind of numbers we're using and what kind of numbers and answers we're expecting to get, whether we're gonna round things or whether we're gonna turn them into fractions before we mess with them, things like that. So we're going to start with rational numbers. Okay? A rational number is a number that can be written as a ratio. Now, to me, ratio means fraction. So if you ever have any question as to whether a number is rational or not, if you can write it as a fraction, it's rational because it's a fraction. Now, the numbers that are not rational are not referred to as not rational. They're called irrational. So we put an IR on the front of this. IR means not rational. Numbers cannot be written as fractions. An example of that everybody knows is pi. Pi does not terminate. It doesn't repeat. Therefore, it cannot be written as a fraction, or it is not a rational number. Rational numbers either terminate as decimals, even if that decimal is just like 5.0000, that's an end. You want 5.0, terminate, and then if it's repeating, 5.13131313, and that's a repeating, that is also something that could be written as a fraction. So it is a rational number. So a terminating decimal, and the reason we use terminate is because it ends. That's why the terminator was referred to as the terminator. He ended things. That's what he was doing. He was running around trying to end. I'm just going to put this big old blockhead on him. There's the terminator. And he's always got those red eyes and anyway, he's kind of weird. But the terminator did one thing. He was supposed to end something. And that end was Sarah Connor. But that is why we refer to him as the terminator. Terminating decimals end. All right? Repeating decimals don't end. They just keep repeating. Now, and by repeating, we mean like 1.666666666, something like that, or 0.11111, all the way out, and it just never stops. Okay, I'm going to give you a couple of examples of that. One example of a terminating decimal is the number 1/4. The number 1/4, if we divide 4 into the number 1, okay, we've got my decimal here, and I put my 0 out front. 4 doesn't go into 1, so there's a 0 there. We bring our 0 down, and then it goes into 10 twice. 8, this is a subtraction now, and now I've got my 8 back there. It is 0 and then 2. I'm going to annex another 0, bring another 0, bring it down like this, and then 4 goes in 25 times. 5 times 4 is 20. That's a subtraction problem. 0. So my remainder now is 0, and here I come down, I bring my other annex, and it's just going to be 0, 0, 0, 0, 0. This has ended. This is a terminating decimal because it ends. The repeat is a 0, and we don't really count that as repeating because there's no value out there. It's just an ending or a terminating decimal. Now, a repeating decimal is something that looks like this. 1/3, and if I divide 3 into 1, I've got to annex my 0, or put my zeros out, my decimal, my 0 up front, goes in 0, and then here it's 3 times, subtract This is a 1, and then I'm going to annex a 0, bring that down. 0, how many times does 3 go into 10? Well, it's 3, and then 3 here, and then 9, and then subtract 1, bring my 0, 0. Yeah, this is not going to end. It's just going to be 0.33333 forever. So whereas this one, we can just tell everybody, hey, this is 0.25, and that's it, because everything out there is zeros. You know, you don't walk around saying that I have $5.00000 in my pocket. I just have $5 in my pocket. You know, unless you're a real cool kid, and then you add as many zeros as you want to, because that's, you know, that's what they do. And then you've got in this case, I can't write all of the 3 down. I can't write all of the 3s down. I just can't. If you write them all out as far as you can take it, and you're like, that's it, I could add another 3, and then we would just keep going forever. So what we're going to do instead is we're going to show that this is a repeating decimal by writing the decimal out, putting a 3, and then putting a bar above the 3 to show, hey, that thing keeps going forever. All right? And that is a repeating decimal. It doesn't repeat with zeros, it repeats with that 3. All right? So whatever is repeating gets the bar here, right? A couple of examples of this, a couple of other examples of this are on page 8 in the book. 5 over 11. Okay, 5 over 11. If we were to put 11 on the outside and 5 on the in, you get 0. 11 is going to go in there 4 times. It's going to be 44, and then there's a 6, and then a 0, and then I'm going to come down with a 5 up here. 55 is going to be here, and then I'm going to have another 5, and then I'm going to have a 6 and a 5 and a 6 and a 5 and a 6. Excuse me, not a 5 and a 6. It's going to be, I should finish this instead of just thinking off the top of my head. Add my zeros. We're going to bring that down. Oh, it's going to be 4, 5, 4, 5, 4, 5 as it repeats. Sorry about the mistakes, guys. So this is a repeating decimal, and instead of doing this, 4, 5, 4, 5, and then marking my repeat, this is redundant. You don't write things again and again. So what I'm going to do is just mark what repeats, and there's my repeating decimal. Okay, my repeating decimal. Some decimals don't end right away, like 1/8. If you divide 1 by 8, you get 0.125 and then a bunch of zeros. This is a terminating decimal. We also use things like this. This is a repeating decimal. I know it's a repeating decimal because I know 1/3 is 0.3333 forever. 2 is a whole number. And if you've never really stopped to think about it, the pieces that are whole go on the left side of the decimal because they're whole. And the other pieces, the 1/3, have to go on the other side. So this is 0.333 all the way out. So what I'm going to do is I'm going to mark the number that repeats, and there it is. Okay? So it's 2.3 repeating. That tells me, because I know what I'm doing, that I could make into a 1/3, and then if I wanted to multiply this by anything, then now I can make it from a mixed number, I can make it an improper fraction of 7/3, and then I can use it for multiplication. But I can't use it for multiplication as a decimal because it is not a terminating decimal. Because you'd have to write all the 3s, and if you use this for multiplication as a repeating decimal, what you have to do is realize that you're making an estimate of your number because there's no way you can write all those 3s out for any answers that you're working for. Okay, that is not all, but I've got one more thing I want to tell you about. Now, a lot of people kind of freak out about, hey, if I've got a decimal, how do I know if it's rational? How do I know if a decimal is rational? Well, here's some examples of things that are rational. The number 5 is rational because it's a fraction. Remember when we were dealing with slopes and we needed to rise over run? Well, look at that. I made it into a fraction. It's a rational number, okay? If I had something like this, 4.25, well, is 4.25 a rational number? Well, can I write it as a fraction? Well, 0.25 is 25 over 100, or 1/4, so this is 4 1/4. Looks like a fraction to me. It's a rational number, right? How about this? This is where things get really kind of sticky. 2.45 repeating. Now, is it a rational number? Yes. The problem is it's not easy to put it into a fractional form. I know it's rational because it is a terminating, or it's not a terminating decimal, but it is a repeating decimal. And repeating decimals are rational because repeating decimals can eventually be put back into rational form or fractional form. And that's what I'm going to do right now. So if we look at some other decimals, like this first, these are very easy to put back into fractional form. And this is what I always say. If you can say the fraction, you can write it down. This is 9/10. There's my fraction. This is 32 hundredths. 32 over 100, that's my fraction. Now, I can simplify this. I can say, well, there's 2 in the top and a 2 in the bottom, so let's make that 16 over 50. There's another 2, so let's go 8 over 25, and we're done. This is 8/25. But all of these are rational numbers. Now, the 0.825 is 825 thousandths. So if we can say it out loud, we can write it down. 825 thousandths. Now, is there anything common in the top and the bottom so that we can simplify that? Well, I know that this is a multiple of 5, and that has a 5 on the end, so it's a multiple of 5 as well. So let's figure out how many 5s there are in that. There's 5 in this, and then there's going to be 40, 60. Okay, so we're going to do 825 divided by 5. There's 1, 5, 3, 2. It's a 6, 30, 2, 5. So 165 over, and there are 200 in that. Oh my gosh, you know what? There was another 5 in there. So we could have divided that by 25 and 25, but nonetheless, we're just going to keep going. 165 divided by 5, if I had $1.65, that's 20 nickels for the dollar, 13 for the 65 cents, and that makes, I just lost my train of thought. That's cool. 20 plus 13 is 33. Well, I hope that's right. And then I'm going to have to check it now. Yep, we're good. And then $2 in nickels would be 40. 33 has the factors of 1, 11, and 33, and 3. And 40 has the factors of 2, 2, 2, and 5. Nothing in common. We're done. Okay, so this is a rational number because I can write it as a fraction. Okay, so what do we do with a repeating decimal? A repeating decimal that we need to make into a fraction. Well, this is kind of long and drawn out, and I'll be honest with you, nobody really does this later on in life when you're like, oh, what do I do with this? I'm a mathematician, and what am I going to do with this special process? Everybody's going to forget how to do this because nobody uses it later. But there's a trick, and I'm going to show you the trick, okay? So let's look first. We should look at if I had 0.37 repeating, okay? Every single time that I do this, I have to relearn it because I really don't ever use it, and I really do know what I'm doing. but I never have to mess with this kind of stuff. So if we're going to look at this, what we're going to do is define this as x equals 0.37 repeating. Then what we're going to do is we're going to take this idea right here, x equals 0.37 repeating, which is 0.37, 37, 37, and forever. Let's multiply both sides by 100. So, because I can do that, because that's kind of things that we do. We can multiply both sides of this fraction by 100. That becomes 100x equals 0.37. And then my 100 over here, what I'm going to come is my decimal is going to move over 37. And then I'm going to have the 37 out here now. So all I really did was take this thing and I moved it over there. And my zero's gone. All right. Now, you guys don't have experience with this, but mathematicians that are a little more sophisticated do these kinds of things for proofs. And you know what? If I took this and subtracted it from this, what if I subtracted 1x away from this side? Well, I would have 99 x's. That's cool. Well, let's take an x from that other side. But I don't want it to be an x. I want it to be that, because that's what x is. And even though we did two-step equations like this, and I told whatever you do on one side, you have to do to the other, this is really doing the same thing to the other side, because that x is really that repeating. So what I'm going to do is I'm going to subtract that over there as well. And so what this does is it makes a zero pair out of 0.37 forever and 0.37 forever. What if we could just knock it off of there? This becomes 37. And all of this becomes a zero pair. Then, if we just divide both sides by 99, here's a 1, x equals 37 over 99. Wow. Okay, so this is our answer. Here's the trick. What if I just wrote that thing down as 37, it's 0.37, so it's 37 hundredths, but it's 37 repeating forever. What if I just wrote it down as 3700? Now that and this are not the same number, okay? But what regulates how much the top of a fraction is worth? It's not the number on the top of a fraction. The number on the top of a fraction never tells you how much the fraction is worth. The thing that tells you how much the fraction is worth, the pieces on the top are worth, is the number on the bottom. Okay? For instance, if we had 4 divided by 4, I have 4 fourths, which is 1. But then when I have 4 over 3, now everything in the top is worth a little more, because we're not talking about fourths, we're talking about thirds. So this is 1, but this thing is 1 over this is 1 and a third. If I had 4 halves, this becomes 2 now. If I had 4 over 1, 4 over 1, this now becomes 4. So as the number on the bottom gets smaller, or gets less, the number on the top becomes a greater value, or it's worth more. So what would I do here to point to 37 over 100 if I wanted the 37 to be just a little more valuable? I would make the number on the bottom 1 less. And if we look at this, that right there, it's 1 less. So when I have numbers that repeat, and they are repeating decimals, and I want them to not be repeating decimals, I want them to be fractions, because I know they're rational numbers because they repeat. What I can do with these numbers is this. If I want 0.57 repeating to be a fraction, if I wrote it down like it was 57 hundredths anyway, which I know it's not, and then just take 1 from the bottom. That's the way the math's going to work out anyway. Now, there are a handful, and you're never going to see them probably, of problems that do not work this way. But they're very, very rare. And I've only seen a couple of them that I messed with. And I'm a little older than you, a little more, you know. So here's another example. If I had 1.6 repeating, What would I do with 1.6 repeating? Well, it's really 1 and something. So let's just put, what if it was 6/10? Well, it's not 6/10 though. So let's just take 1 from the bottom. So this is 1/2 If I had 0.4 repeating, well, let's just pretend it's 4/10 for a moment, but I know it's not 4/10. So let's steal 1 from the bottom to make the 4 worth a little more. This becomes 4/9, and it works that way for every problem that you're going to see. All right, so I think I'm done with this. I'm going to make a different video now, different subject. I'll see you soon. Meow, meow.